Hello everyone and welcome to Frida. In this video, we will continue solving the 8K SEC iOS reverse engineering challenges. After completing the first two challenges, Frida in the middle and Twizzle Me Timbers, we will now focus on the third challenge, which is Trace the Map. As per the description, it says Trace the Map is an iOS location based challenge where you must collect 5 hidden map markers scattered within a 1 kilometer radius. Each collectible is worth 100 points and you need all 500 to win. Get within 50 meters of each collectible to score. Sounds simple, not so fast. While spoofing your GPS might seem like the obvious path, this app comes with a few built-in countermeasures to detect foul play. Okay, so the goal over here is to score 500 points by collecting all 5 hidden markers using clever spoofing, patching, or dynamic instrumentation. And we have two restrictions for this challenge. First is that the win page is only after scoring 500 points. And second is that the app performs runtime checks to detect spoofing and other manipulations. So we have to be careful about that. So essentially, this app expects us to physically travel to the locations marked within it in order to earn these points or scores. Each valid location awards us 100 points, and the total score required to complete the challenge is 500 points. And the app also clearly states that GPS location spoofing is not allowed. Of course, on a jailbroken iOS device, the easiest approach would be to install a tweak that can fake the device's GPS location, but that's exactly what this challenge is trying to prevent. This being said, we will still try to spoof the GPS location just out of curiosity to see whether the application is actually able to detect the real location even after spoofing. But before that, let me show you first how this app looks like. So I have already downloaded and installed this application on my jailbroken iOS device, TraceTheMaps, as you can see here. And upon launching it, we will get this screen where it shows the map along with my current location. Of course, this is not my exact location where I am sitting right now, just in case you are thinking where am I currently. And these are the 5 different places this app wants us to travel in order to score the points. Currently, our score is 0 out of 500 because we are nowhere near these locations, right? Alright, so let's try the first attack, which is very obvious, that is by spoofing the location. So on a jailbroken device, you can use any package manager which you have installed. For example, I am using Celio package manager, and inside Celio you can search for any GPS spoofing tweak, fake GPS, and you will get couple of options. I am using this one, fake GPS, which I have already installed, right? And it allows you to fake your GPS locations system wide. Okay, so once this is installed, you will get this fake location tweak application on the launcher, and when you launch it, it will show you your current real location. So in this case, this is my real current location, and you can spoof your current location anywhere on the map by simply selecting a location, let's say this one. So you just need to tap and hold that location, and that will be set as your fake current location. Once you have set your fake current location, we have to enable the service by simply toggling this button from the top right corner, and now it shows the fake address we have selected, right? Let's confirm this by opening Google Maps, and indeed it's showing the spoofed location instead of my real current location. This confirms that the GPS spoofer is working. Now let's again launch the TraceTheMaps application, and here still it's showing my current location and not the spoof one. This means that somehow this application is not affected by the spoofer, which is very interesting. This indeed confirmed that we cannot use spoofing tweaks to solve this challenge. If you are interested or curious about knowing how this application detects the spoof and grabs the true location anyway, drop a comment below if you want a deep dive video breaking down their exact technique. Okay, so at this point, the only option left is to reverse engineer the application to understand how it handles location verification and score calculation. So we can either spoof the location internally or modify the logic that awards points. Let's dive into the real analysis now. Okay, so here under this directory, I have already downloaded the IPA file. And as most of you already know, that IPA file is nothing but a zip archive containing all the artifacts and resources, including the executable binary files. So what we can do first is change the extension of this file from .ipa to TraceTheMap.zip, right? And then simply use the unzip command to extract the zip file. Once done, you will get this payload directory where all the artifacts, resources, and the actual binaries are located. So let's go inside this payload directory, and here you will find this tracethemap.app directory. So we have to go inside it to see its contents. And as you can see over here, we can find all the artifacts and the resources which are packaged under this IPA file. Then we have these two main files, TraceTheMap and TraceTheMap.debug.dylib. So these are the two main binaries, and based on our previous analysis done on other challenges, it was observed that the core business logic usually resides in the dynamic library and not in the main binary file. This main TraceTheMap binary file is just the wrapper for this dynamic library. All it does is load this library dynamically into the memory when the application is launched. So instead of looking into how this is being done in TraceTheMap binary, we will directly start analyzing this dynamic library. And as you know, to analyze any native library, we have to open it up into a disassembler to see what's going on inside it. You can use tools like Ghidra or Radare for this, but in today's video, I will be using IDA to disassemble it, mainly because IDA is more mature and generally handles Swift decompiled code more robustly. So here I have already opened IDA, and when you open it for the first time, you will see this interface, and by clicking on this and from the quick start panel, you can simply click on this go button to open its interface. So if I go into Finder under trainings 2025 under iOS directory, I have 8 KSEC challenges, inside which I have challenge 3 where I have extracted the payload, and inside that we saw that we had that TraceTheMap.app. So this is the same package which is a directory, so we can see the contents of it, and inside that we have this dynamic library, right? So let's just drag and drop it into IDA interface, and as you can see, it has automatically identified that it's of Mako file type, automatically selected the processor type as well. All you have to do is click on OK, yes, and the analysis is started in IDA. And because the library is pretty small, the analysis is already done, and now you can see a nice disassembly in this disassembly view. All right, now we have to start looking into stuff in IDA so that we can gain some information about this binary. So let's begin with string sections. So if you click on this view, go to open subviews and click on strings, it will generate a list of strings for you. So all the readable strings which are hard coded into this dynamic library will be visible over here. So at first you can see these are some headers followed by some library paths. Then we have some function names, some garbage strings, then some strings like location manager. Let's see if we can find something related to location itself, because that's where the main logic lies, right? So over here we can see that latitude, longitude, latitude delta, user location, location manager, these type of strings are present. Also there is this location manager, so this could be the class responsible for dealing with the location related logic. So let's see if we can backtrace things from here. Let's begin with the latitude and longitudes first, because anyhow in order to determine the current location, latitude and longitude needs to be identified, right? So let's see, by simply double clicking on it, it took me to the place where the string is defined. Also by clicking X, it will show you the cross references to that particular string, and as you can see, it's being referenced from this place, which is not a function. So let's go back. Similarly for latitude, longitude, nothing can be cross referenced. Let's also see for location manager because this is also interesting. But again, it's taking us back to Swift field, so nothing we can do over here. Let's go back to strings tab and let's see what else we can find. Trace the map challenge, walk or spoof to find hidden collectibles. So these are the strings which are visible on the UI of the challenge. So we can also start from here, but that would be a lot of UI related code which we don't really want to get into. So let's skip over them. Then we have getting your location. Okay, so this is interesting one. We can keep this in mind. Let's see if we can find anything else. Over here, there is this distance from location string. This looks interesting because if you think about the task, the app has to calculate the distance from our current location to the desired location, right? So this looks like a promising starting point, and let's try to find the cross references to that string to see where and how it is being used. So this string is being referred from this address or this function basically, which is content view dot check proximity. And if I double click on it, it will take me to that function and show me the disassembled graph of it. Here we are inside content view dot check proximity function, and just by the name of this function it makes sense. So it's an exported function which takes one argument which is of type C location, right? So C location, as you can see, I already passed it and identified that it's of type structure. So it looks like in Swift basically you have classes, right? So this could be a location class, and that object is being passed to this check proximity function. So by looking at the signature of this function, we can assume that it's either taking user's current location as its argument or the desired location this app wants us to travel to. And in the disassembled view, actually I can see lot of Swift UI related code over here along with Swift runtime code. So this makes analyzing the disassembly a bit more difficult. Instead, what we can do is we can ask IDA to generate a decompiled code for this function. But remember that the decompiled code is based on heuristics, and depending on how the code is compiled and which language is used, we may see lot of extra code. So we have to be careful while analyzing or understanding the decompiled code also. So to instruct IDA to generate decompiled code, we can simply press F5, and then as you can see it has opened a new tab with the name pseudocode A. So basically this is how IDA generates a high level pseudocode which is much more easier to read and understand, right? So as you can see that the decompiled code is not that big actually, and in fact a significant portion of this code is not relevant to the core business logic. Most of what you are seeing over here is automatically generated by the Swift compiler during compilation. So to understand the real logic of this function, our first step is to identify and filter out the code that isn't part of the business logic while still having a basic understanding of the Swift compiler's runtime behavior. Don't worry if it looks scary. I will try to explain as much as possible about Swift runtime, and we will try to filter out the code and try to extract the real business logic out of it. So these are just the variables, stack variables declared or defined by IDA during decompilation. Okay, and then it's assigning the values to those variables, right? Then here the very first line you can see is this one, v56 is equal to type metadata accessor for collectible. This line isn't part of the actual business logic of the function. Instead, it's related to the Swift runtime. As of now, we don't know what this collectible is. So basically, by this instruction, trying to understand what type of data or what type of object or what type of data type this collectible is and how it's laid out in the memory. So you can think of this v56 variable as a pointer pointing to the memory location where this collectible is laid out in memory. Most likely it would be a custom list of collections, something similar to structure in C programming language. Why I am saying this is because if we go back to the challenge description, here it refers each of these locations as a collectible, right? So this could be that collectible object. Then we can simply skip over these lines, and then the next interesting one are these two lines. Again, you might think these are the important ones, but they have nothing to do with the actual logic of the function. They exist purely because of Swift's memory management model. Basically, whenever an object is used, Swift inserts retain and release calls. So in this case, state collectible is a Swift UI property wrapper, and Swift needs to ensure that it stays alive. So this line basically means keeping a counter for the object so that it does not get deallocated when the function is being executed. Moving on, we can actually skip over them as these are not the important ones. Then we have these lines. Now these lines are quite important. I will explain you why and what they are doing. So first let's begin with V66 Swift instantiate concrete type from mangled name for type metadata for collectible array. Right here, this very first line is actually responsible for querying the Swift runtime about the concrete runtime metadata or information for the type collectible. So basically this metadata will describe about the collectible array's element type, how to copy, retain, release and iterate over this array. So this line is all about type resolution, and that information will be stored into this v66 variable. Now why I said that it's a collectible array is because of these square bracket. That's how an array is represented in programming languages, right? Then let's take a look at the next line, which is random access collection dot indices dot getter. Now this is the first real logical operation. You can think of this as collectibles dot indices in Swift programming language. What it does is it computes a range, stores it in v95 variable. So this range is usually something like 0 to length of the array. So that range information is now stored into this v95 variable. Then we can skip over these as these are about Swift runtime, so not required for us. And then we have collection dot make iterator. What it will do is it will create an iterator over the range. If I have to show you how it would look like in high level Swift programming languages, it's something similar to a for loop for index in collectibles.indices. So that's how the actual code would be, and after compilation this is how it is now. So here it's basically creating an iterator object so that it can iterate over each of the element of the collectible array. And if you observe this v72 variable, it's actually storing the information about the range, right? Once this is clear, the rest of the code is pretty easy to understand. So far, basically what has happened is that at the beginning, it has created an object v56 which is containing the information about the collectible class or object, right? Then at this time, it's not a concrete information, it's just a metadata about the collectible. But after this statement, initiate concrete type, that information is converted into a usable real information, where at runtime all the information about the collectible array is resolved and stored into v66 variable. Then using random access collection dot indices dot getter, it's actually identified the range of the collectible array, like how many elements are there in this collectible array and things like that, and stored it into v95 variable. Then again the range is resolved. Then using make iterator, it's creating an iterator object so that we can iterate over each element of the collectible array one by one. Then we have this infinite while loop. So all this code is running inside an infinite while loop, and this is where the real logic or the real magic is happening. Now inside this while loop, we have this indexing iterator dot next. This line simply advances the iterator to the next element in the array, something like I++ in the for loop, right? And each time it's executed, the loop moves forward by 1, pointing to the next item in the collection. Then you can see this if condition. If v91 and 1 is not equal to 0, then it will break out of this loop. So you can think of it as a terminating condition. If there are no more elements in the array, then it will terminate this while loop, right? Moving on, we have this code. Again, these few lines have to do with Swift runtime. So this is similar to what I explained earlier. It's asking Swift runtime to retain collectible object in memory. But this particular line is important. Array.subscript.getter. What this means is that it's trying to access a specific item from the collectibles array. So this is the actual data access. You can think of it as item equal to collectible index in Swift programming language. So this instruction would be translated into something like this in high level Swift code. And why I am saying that it's trying to access a specific item from the collectible array is because if you see, it's taking v49 variable as one of its argument, and v49 is nothing but v53 variable, which is nothing but v90, which is containing the next element of the collectible array using this indexing iterator dot next, right? So here, using this array.subscript.getter, it's trying to access that element which is pointed out by the address stored in this v90 variable. So here basically v49 is the index, v50 is the actual array, and v56 is pointing to the metadata of collectible in memory. So if you backtrace this v56 variable, it's initialized over here at the beginning, right? Where I already explained what it's storing. It's storing the metadata information about the collectible. And when I say v56 contains metadata is because v56 contains information about where each field of the collectible is located in the memory and how big it is. So all that information is part of the metadata which is being stored into v56, which is obviously required in order to access a specific field from the array of collectibles. Then this line v51 is equals to unsigned int 8 v61 typecasted to integer pointer v56 plus 28. Again, very important because it's trying to access a specific field of the collectible and storing it into v51 variable. Let's start with the inner part first. v56 plus 28. So we already know by now that v56 is containing the metadata information about the collectible, and here it's adding 28 bytes to v56. So by default, v56 is pointing to the very first field of the collectible structure, and by adding 28 bytes, it's trying to read whatever the field located at 28th byte. Obviously, just by this information, we cannot tell yet which field it is and what is its size, but at least we know that it's trying to read a specific field from collectible structure. Then whatever the data located in that field is being converted to integer pointer. Let's break it down. So basically integer pointer is telling the compiler to treat the address pointed by v56 plus 28 as a pointer to integer, and then using this pointer it's going to act as a dereference pointer. In simple term, it is telling compiler to read the value located at v56 plus 28 as integer. And if you have noticed here, we have square brackets on top of it. This is usually how we access items from an array, right? So whatever the index or the integer value returned by this, that particular index will be accessed from v61. So v61 should be the collectible array. Let's see. So if we try to see where v61 is initialized, it's initialized over here. Okay, so this is how Swift usually allocates temporary stack space for a value type. In short, we can say that v61 is pointing to the base address where collectible is stored on the stack. So if I have to convert this one single line into more readable form, it would be some field equal to collectible dot some field. I think this will make more sense now. We are trying to access some field from the collectible structure and storing it into a variable. Okay, and then one last thing is that whatever the value returned by the collectible array at that particular index will be typecasted to unsigned integer 8. So it's nothing but 1 byte. So this is a very useful information. This is telling us what is the size of that particular field that we have accessed. So at this point we can say that this field which is being accessed is of type boolean, because in Swift usually boolean data type takes 1 byte. So this v51 variable is containing the value of that field at the given index in the collectible array. Moving on, we have this if condition, which is actually comparing the value of v51 variable by performing an AND operation and comparing it to 0. So this indeed confirms that this v51 value is of type boolean because it is being used in a if comparison. So basically, if this v51 contains 0, then the AND operation result would be 0 and this if condition will become true and the if block will be executed. And if v51 contains 1, then this if condition will fail and all of this code or the if block will not be executed. So we can say at this point that it's some kind of a check inside the collectible structure. Let's now see what is happening inside this if block. Maybe it will give us a better idea on the core logic behind this check proximity function. So inside it, we can see that the very first line is type metadata accessor for C location. This is similar to what we had earlier, right? It's basically asking Swift runtime about the information of C location. So we can say that v38 is pointing to the location where C location is stored in memory. Then we can skip these as it is mostly related to Swift runtime logic. Then we have array subscript dot getter. So I hope now you are familiar with this statement. It's basically trying to access a specific item from the array, right? So here v49 is the index, v44 is the array itself, and then v56, which as we know that it's containing the address pointing to the metadata information about the collectible. Or in short, we can say that it's pointing to the first field of the collectible structure. Then the next line is again what I have explained earlier over here, right? So let's begin with the inner part first. So this time it's adding 24 bytes to v56. Last time it added 28 bytes, but this time it's adding 24 bytes. So this must be the field 4 bytes before the last one. And here it's converting the overall value to Swift double. This means that this field contains floating point values and not just some decimal values. And whatever this value is, it's going to be stored into this v41 register or variable. So at this point, now we know that the second field of this structure is of type double, and double usually take 8 byte in memory. So v51 variable is holding a double value. Moving on, let's skip these, and then we have again array.subscript.getter, and over here again you are familiar with these arguments by now. Let's see what this instruction is doing now, starting from the inner part. So here this is the previous field, this one, right? And it's adding 8 bytes to that field. So like I explained, double takes 8 byte in memory, so it's trying to access the value or the field which is after 8 bytes. So this would be the next field after this one. So what we can say in short is that here it's trying to access the third field from the collectible structure, and again it's being converted into int 128, which is nothing but again of type double. Okay, so far we have identified 3 fields of the collectible structure. First one is this one, another one is this one, and the last one is this one, right? Let me try to represent it in a high level programming syntax. So that would be collectible field 1 of type double, field 2 of type double, field 3 of type boolean, right? Okay, this is just for your reference so that you can keep this collectible structure in mind, how it looks like, how it's laid out in the memory. Okay, let's proceed further. After all of this, we can see that this particular statement, C location dot allocating init latitude longitude. So it's pretty easy to understand, right? By looking at this, we can say that here it's trying to initialize the location class or object, which is taking latitude and longitude as its two arguments. So V41 and V42 variables are nothing but latitude and longitudes respectively. And this is what we have anticipated over here. The result of this field, which is of type double, was being stored into V42, which is passed over here as longitude. Similarly, V41, which we have resolved over here of type double, is being passed as an argument over here as latitude, right? So we can say that in the collectible structure which we have represented over here, field 1 is nothing but latitude, field 2 is nothing but longitude, right? Cool. We have almost all the information now about this collectible structure. Then finally we have objective C class distance from location, right? This is how IDA decompiler interprets the objc underscore message sent. We can confirm this by looking at the disassembly. So if I go back to the disassembled view of this function and try to see where this distance from location is being called, it's over here, right? And here you see that this function distance from location is being passed to the objc message send. Here basically this function objc message send is trying to call distance from location, which is an objective C method. So it's an indirect way of calling a function instead of directly calling it. Now this is the key piece we were looking for, because it's taking V45 variable, which is nothing but an object containing latitude and longitudes. And by the name of this function, distance from location, it should calculate the distance between two locations, right? And the result of that function is being stored into V46 variable, which is then being compared over here as if V46 is less than 50. So if V46 variable, so basically whatever the distance returned by this function, if it is less than 50, then this if block will be executed, otherwise not. And again, if you look at the challenge description, here it explicitly says get within 50 meters of each collectible to score. So now this logic makes more sense. Here it's basically trying to compare the distance of user location with the collectible. If it is less than 50, then inside this the main thing is over here, it's basically adding 100 points to your score. So if your distance is less than 50, it will give you 100 points. Cool. So now we know most of the things in this check proximity function. We know exactly where the score is being added. We know exactly the condition based on which the score is given. We know the function which is responsible for calculating the distance between the two locations. So all we have to do now is to come up a way in which we can manipulate the result so that the distance always comes less than 50 meters. And yes, if you are familiar with dynamic instrumentation, we can simply do this by hooking this distance from location function and manipulate its return value. So for hooking, as usual, I am going to use Frida framework. So let's start writing our hooking script. Let me go to the terminal, clear this out. Let's go back 2 steps and let's create challenge3.js as our hooking script. Now inside this, what we have to do first is a sanity check. So let's put a if condition and make sure that when we launch the application using Frida, we will get the objective C runtime. So using objc.available API of Frida, we can make sure that the objective C runtime is available. Otherwise, we can simply skip hooking logic. So in the logs console.warning, let's just print that objective C runtime is not available. Now inside this if condition, let's start by first resolving the class name where distance from location function is coming from. So this distance from location function is actually part of the CL location class. So what we can do is we can create a variable with the name CL location. You can name it anything else. It has nothing to do with the original class name. Then by using objc.classes, it will give us a list of classes which are currently being present in the Objective-C runtime once the application is loaded into the memory. And then using another dot operator, we can specifically mention which class we are looking for. In this case, we are looking for CL location class, right? Then let's create another variable called method. Then this CL location variable is now pointing to the address where actual definition or the actual information about the CL location is present in the memory. So using this CL location variable, we can access the method inside that class. So the method name is distance from location colon. Okay, so now this method is pointing to this distance from location method. Now using interceptor.attach API, we can actually hook this method by passing method variable which is containing the address or the implementation of this distance from location function. So by using the implementation, we can tell interceptor.attach API where to hook, and then inside on enter, and another one is only. So on enter will be called as soon as the function is called, and only will be called when the function is about to return. In this particular case, we want to manipulate the return value of this function, so we don't really need to do anything inside on enter, but just for understanding and troubleshooting purposes, let's put some logs over here. So this distance from location method is actually, as I explained earlier, is getting called from objc message send, right? So this objc message send function basically takes three arguments. First one is the self pointer, second one is the name of the function we want to call, in this case it's distance from location, and then the third argument of this objc message send function is the arguments which needs to be passed to this distance from location function. Okay, so over here let's just access the self pointer. Maybe that would be helpful later in case we need to troubleshoot anything. And as all of this is part of objc runtime, so we have to represent everything as objective-c objects. So for that, what we can do is simply call objc.object and put the argument over here. So what it will do is whatever the data located at this address pointed out by the first argument will be typecasted or represented as objc object, which is the ideal way of reading or processing the arguments in Objective-C methods. Then the second one is the, let's name it as other, again converted to objc object, and instead of the name of the function, I want to take the arguments which are being passed to distance from location method, which is in third argument, which we can access using second index, right? Then let's just simply put the logs which says distance from location followed by the arguments. First one is going to be self, then second one is going to be other, and I'm going to convert it to string. Maybe let's do the same for self, that would be more readable. Okay, then coming to only. Inside this, let's first store the original return value. Now we cannot simply do this in this particular case. Why? Let's go back to the disassembly, and here, as per ARM calling convention, usually the result of the calling function is stored into X0 register, right? But in this particular case, if you observe, the result is actually stored into D0 register. If you try to access the complete X0 register, then you will not get the exact return value. It will contain extra bytes which might not give you the correct result. So let's be specific and mention the 0 register over here. So let's just print this value. Original distance is equal to original. And what we want to do over here is we want to manipulate this the 0 value or the return value to something less than 50. Let me just make it 0. Modified distance is equal to this dot context dot d0, right? That's all. So what will happen over here is as soon as this distance from location function is called, on enter will be triggered, where it will print the original arguments which are being passed to objc message send and also to distance from location method. And then when the function is about to return the distance after calculation, on leave callback will be executed, and inside this we are logging the original distance and the modified distance. So now if everything goes well, whenever this distance from location method is called by the application, our hook will be triggered and it will always return distance as 0, which is obviously going to be always less than 50. So let's save this script, clear this terminal and launch the application via Frida. But before that, I need to activate my environment, and now using Frida-ps-uai, I am first going to copy the bundle ID or the package name of this application, which is this one, com.8ksec.traceTheMap. Let's just copy this, clear it out, and then again using Frida-u-l, the name of the script, which is challenge3.js, followed by -f to forcefully spawn the application, and then the package name. Now before executing it, let me also show you the application. All right, so yep, this is the current state of the application. Let me just try to launch it again using Frida, and there you go, we got the you win screen. You have collected all 5 flags, and in the logs you can see that our hook is being triggered, and here it's showing us the arguments which are being passed to distance from location. So these are the coordinates followed by the speed. So whatever is being passed to this distance from location function is being logged over here, and then the original distance was this, which we have modified to 0. Awesome. We have successfully solved challenge 3, trace the map, and I hope you learned something new in this, specifically in terms of how to handle or deal with a Swift compiled binary.